We now know how to estimate the width in the neural network models. However, you may already notice that it is actually difficult to program the algorithm. Particularly for neural network models, if we have hundreds of parameters, it will be much more difficult than the simple example I just showed you in recurrent analysis. Fortunately, there are many or several popular machine learning libraries or packages that can help us build the neural network models as well as help us estimate the parameters in the model. Among them, TensorFlow and PyTorch are probably the most popular packages used in both industry and academia. TensorFlow has a very steep learning curve to me, but fortunately, a package called keras that provides a high-level API to TensorFlow. Using keras, we can actually build the neural network models very easily. Although keras was initially developed as a Python package, but we can now use it within R2 because we have an R package that can connect to keras. Installing keras or setting up keras in R is actually not that easy. We can actually fail very easily to install it. If you want to install keras on your own computer, you can follow the instruction first here. And if the instruction didn't work, like myself, when I followed the instruction to install keras on my computer, it didn't work out. In that situation, you can use my instruction here. So when you use the instruction on RStudio, it actually provides an automatic procedure or automatic methods for you to install the packages. But if it didn't work out, you can install that step by step, like what I did here. And first, you can install Python. This step usually is straightforward. And after you install Python, you want to install the TensorFlow package for Python directly. Once you have installed the TensorFlow successfully, then you can move forward to check whether your TensorFlow is installed correct or not. You can run this example here. After that, you can open R and first install the TensorFlow package using the install.package function. After you install the TensorFlow package, and then install the keras package. If you follow those steps, most likely you are ready to use the keras package in R to do neural network data analysis. If the setup of the keras is still not successful, you can still use something called Google Colab here. Google Colab basically provides the environment for you to try out the different machine learning algorithm. To use Google Colab, you need to follow this link. Notice that particularly add the option language equal to R. What you can do is you can actually direct copy the link and then open that in your web browser. Since most likely you are going to use this, I'll show you how to do it here. So you can go open your web browser and then input the link. It will need you to have a Google account to use it. So once you open, it has an interface look like this. In this interface, you can use it as you are using R or RStudio, for example. If I want to generate 10 random numbers, I just type the code normal 10, and then click here to run it. And then give you the 10 random numbers. You can add text. In Google Colab, and then you can add code here. Keras is not installed automatically on Google Colab. If you want to install Keras, you can do this. Install package Keras. And then it will install Keras for you automatically. And it will take some time, but it's much easier than setting this up on your own computer. All the code I'm going to show you in this workshop can be run on this Google Colab. All you need to do is just copy and paste the code into the web page here, or the web interface there. And if you only run neural network analysis a few times a year, or your purpose is to learn how to use the neural network models, then you don't need to install the Keras on your own computer. You can just use Google Colab. I just showed you. Now let's see how we can fit the neural network model to our active data. I'll come back to my PDF file. The model we are going to use is this one layer neural network model I showed you earlier. Again, like for this model, we have 4 predictors, or the 4 input. Remember, this x1 represents 3 input. Okay, x11, x12, x13. And then we have one hidden layer with 32 nodes. We have one output layer with 1 node only. So this is the model we are going to use. Before I build a model, where I want to process my data first. Most importantly, I need to change my data into the matrix format. Remember, our active new data set is a data frame, but the keras package cannot directly take a data frame as the input. So therefore, I want to first transform my data into the matrix format. It can be done simply use the s.matrix function. I also split my data into training data and test data. For my training data, I have input, I call it x.train. I have output, y.train. So therefore here, x is n by 6 matrix, and my y is n by 1 vector here. So this is my training data, and this is my test data. Both training data and the test data are in the matrix format. Next step, I need to build my neural network model. In regression analysis, we know we can use linear model, something like this, where regress on x. The keras basically provide something very similar to this to build a model. To use the keras package, we first need to load it in using the function library. Notice that here I set the random number seed. The reason I do this is because I want to replicate the data analysis in the future. And if you don't set the seed for your data analysis, each time you will get slightly different results. It's more like a random number generator. Each time you will get different random numbers if you don't start from the exactly same place. To set the seed, I use this set random seed function from the TensorFlow package. And my seed is the current date of this workshop. So I use this here. Okay. Once I set up this, you may need this like every time. Certainly, you only need to load your library once if you are using it like the whole time. There are different ways to build a model in using keras. Here I use the sequential method. To use the sequential method, I use the function keras model sequential. Building a neural network model using sequential method is like to build a Lego. So basically, in building Lego, we know we add each pieces on top of the other pieces. So the keras model basically does the same thing. We add different layers to this model. So we start from here means we want to build a model sequentially. And then I use the pipe operator. Pipe operator means I can keep adding code to the model. In our neural network model, we know we have the input layer, and then we have the hidden layer, and then we have the output layer. Since we are building the model, we need to add those layers to the model. When you use the model sequential method, you don't need to explicitly specify the input layer. So which means the specification of this layer is not necessary. So therefore, our first layer to specify is actually the hidden layer here. How to specify this hidden layer? I use the layer dense function. In the layer density function, I need several different options. The first option is the units. The units gives the number of nodes in that layer. So in this layer, we have 33 nodes. Therefore, I set units equal to 33. Another information I need to give is the input shape. The input shape basically tells the information about the input. In our example, we have 6 columns in our input. So therefore, I need to tell the input shape is 6 here. And this 6 can also be directly calculated from my data as in column X training data. In this situation, I don't need to specify a number each time. Another option I need to provide is the activation function. Here, my activation equal to linear, which means I'm using a linear activation function. So basically, this specifies the first layer, hidden layer. And as we know in our neural network model, we also have an output layer. So output layer, again, add another layer, add another Lego block to my Lego. In this case, I use layer dense again. So my units equal to 1 because I only have 1 node in the output layer. My activation function here, again, I use a linear function. except for the first layer here, we don't need the input shape in the layer dense function. The reason is because the layer dense function will automatically look for the input shape from the previous layer. So that's why we use the PEP method to specify the model. So basically, once we specify this, it will calculate the input shape and use it here. Now this is my model. I call my model as MODNN. And if you want to look at the information of the model after you specify it, you can directly type the name of the model here. Once you type the name of it, the output will look like this. So that's a sequential method. And then we have a layer, and then output shape, and the number of parameters associated with that layer. In our situation, the first layer is called dense one. You can also specify the name, but here I just ask the program to generate the name for it. So that's the first layer. The output shape is 32. Whether the case, remember in our first layer, we have 32 nodes. Right? Our input shape, we have 6 columns. So our data, we have total number of participants and total number of variables. Our training data actually has only 2,000 participants. Right? So therefore, our training data has a shape 2,000 times 6. So that's our input data. In the input, for the input shape, we only care about the second one. So that's the number of columns. The first dimension is also calculated directly, automatically by this function. So that's our input. Our input with the data, and the input will go through the first layer, through the width. So this is the input times 6. And then we have the width. The width are the passes, the fully connected passes from each X to this 32 each, we have a width. So in total, we have this number of widths, which means once we feed the data into this neural network analysis, this is input, multiply that width, we get the value for the hidden nodes. So which means if we multiply those two matrices together, we have a matrix with this dimension, 2,000 times 32. So that's why it says the output shape has 32 columns. The first dimension is none because we don't need to specify the first dimension. I'll explain a little bit later. Okay. Then it gives you the number of parameters in this layer. How to calculate the number of parameters? Look at the model again. Those are fully connected, right? So we have 6 input, 32 nodes here. So in total, we have 6 times 32 weights already. But remember, for each node here, we can also have an intercept, or we have a bias here. So we have another 32 parameters. So the total number of parameters will be 32 plus 32 times 6. So that's 32 times 7. So in total, we have 224 parameters. That's the first layer. Now let's move on to the second layer here. For the second layer, so there's only one output. So the dimension is 1. But notice that we also have all those widths, 32. So that's 32 times 1 width. Right? So move from this nodes to this output nodes. So we basically multiply the input and the width together again. So this is width, so this is input. So therefore we have 2000 times 1 dimension. So that's the one here, output here. How many parameters we have? We have 33. Why 33? Because we have 32 nodes, 2 widths here, plus 1 intercept. So in total, we have 33 parameters in the model. Adding them together, we have a total of 247 parameters. Notice that even for this very simple neural network model, we already have a large number of parameters. Recall in the regression analysis, we only have 7 parameters, but here we have 257, which means the neural network model here is much more complex than the regression model we used earlier. Again, I talk about how to calculate the number of parameters. Now we have the model. Eventually, we want to estimate the model parameters, the width and the base. How to estimate the parameters? To estimate the parameters, we first need to compare our function, to use the compare function. The compare function basically will specify all the information regarding the algorithm we are going to use. For example, first thing we want to specify is what kind of criteria we need to use to minimize the target function. Or the first thing we want to use is what kind of like objective function we want to use, also loss function we want to use. Here I specify loss equal to MSE. The reason is because we have continuous data. I basically look at the difference between the output and Y here. So MSE is mean squared error. So we are going to minimize this to get the parameter estimate. Then I need to specify what kind of optimization algorithm I want to use. There are many different kinds of algorithms in keras. But in this case, I just use the RMS Prof algorithm to estimate width. Earlier, I also talked about we can specify learning rates or learning rate in our algorithm. Here, I set the learning rate to be 0.00001. Again, you can change this to a different value. And finally, I want to see how to evaluate the performance of the model. I use mean absolute error to evaluate the performance of the model. So by specifying those options, I now have a model with a way I want to estimate it. Notice that I put everything again into this model. I use a pipe. This basically means I add the extra information to this model. So here I specify the model. Now I add the estimation method to the model. Now I already have a model. I have my algorithm. I have my optimization algorithm. Next, I really want to estimate the model. In regression analysis, we know we can use a linear model to estimate the model, to fit the model. Now, I want to fit the neural network model. To do it, I'm going to use the fit function. The fit function actually carry out the fitting process. It carry out the iteration process I showed you earlier for the very simple example. In this fit function, I need to provide my data, training data here. So I call it like X train, Y train. This is the outcome, and this is the input. I need to know how many iterations I want to run my algorithm. Here I set the epochs equal to 50. The epochs basically gives the total number of iterations you want to use in the algorithm. I also specify something called batch size equal to 32. What does the batch size mean? Remember, in our original data set, we have 2,000 participants, which means we have 2,000 rows. And they have 6 variables. In this situation, if I set this as input, each time it passes through the hidden layer, I need to do the calculation as this matrix multiply this matrix. Right? And when you have 2,000 data, 2,000 rows of data, this is still not that difficult to do the calculation. But if you have 2 million or 2 billion data, the calculation can become very difficult. In this situation, you may want to use a smaller value instead of doing the calculation for the whole 2,000 participants. How about I only do this for 32 participants? And in this situation, multiply those 2 matrices together is much easier. Another more important reason we do this, we only use a part of the data, is we can do parallelization. Nowadays, we often have computers with multiple cores. We can also have GPUs with thousands of cores or hundreds of cores. Each core can do the calculation independently, separately. So therefore, what we can do is we can break a large data set to be smaller parts. For each part of the data, we can do the calculation on one CPU core or on one GPU core. If we do this calculation simultaneously, we can reduce the time to do the calculation. So therefore, here the batch size usually we specify a smaller number here. Now let's go back to the table here. Remember earlier, it says the output shape equal to 9 here. The reason is because this shape, the number of rows depends on the input. So now if my batch size is 32, so this will be 32 times 32, right? And this will be 32 times 1. Okay, so it's not necessarily 2,000 here. Another option I used here is called validation split equal to 0.2. What does this mean? In estimating the width, we need to use our data. So our training data can be used all together in estimating the width. But a neural network model oftentimes would overfit your data, which means if we can specify a complex enough model, we can estimate or we can fit each value in our data set exactly. in this situation, you won't have any error in your prediction. But the issue with the overfitting is if we want to apply our model to a new set of data, then the prediction can be very bad. Right? So therefore, when we estimate the width or the parameters for the neural network model, we hope we don't overfit the model too much. We hope we can predict the outcome using the new data good enough. The idea of the validation split is I'm going to split my training data into two parts. Remember, this is my training data. My training data, I have 2,000. I again split this into two parts. One part is to estimate the model. And again, you can call this is the training data to estimate the model. And then another part is called validation data. This part of training data is actually estimates the weight. Okay. This validation data is actually to investigate whether we can predict the data from a new data set well enough. In generally, when we fit the model using the training data with the increase of iterations, the loss function would always become smaller. So which means we can predict the data in the training data better and better. However, since we are overfitting the data, for the validation data, the loss is in general would first decrease and then increase with the increase of the number of epochs, also number of iterations. So if we look at the plot of that, okay. So if this is a loss based on the training data, it will look like this, becomes smaller and smaller. But if you look at the training data, validation data, most time will look like this. The loss will first decrease and then increase. In deciding how many epochs we want to use or how many iterations we want to use, we want to choose a value we want to choose a value that give a trade-off between the prediction for the training data and the prediction for the validation data. So in this situation, probably we can choose a number of epochs here. It gives us the loss value for the training data here, but give us the loss function value for the validation data here. So in this situation, we won't overfit our data too much. We can still have good performance in future prediction. For this particular example, after I fit the model here, after I run the code here, I can take a look at the performance statistics here. In this plot, basically I have the loss function value for this is training data and this is validation data. Okay. Remember, I also use a different matrix here. I use mean absolute error as the matrix. So therefore, I also have the value for the mean absolute error here. The mean absolute error can also be used as the loss function to select the number of epochs. Based on the plot as well as based on the values of this loss function and the mean absolute error, I found that maybe I can just use 20 epochs. Here, I would get like good enough results to use So therefore, I refit the model with 20 epochs. Oftentimes, you need to refit the model with a selected number of epochs because, as I mentioned earlier, so if you look at your validation data, maybe after the 50 epochs, the validation error is actually very large than the validation error here. So certainly you don't want to use the results from 50 epochs. You want to use the results from the 20 epochs only. So that's why I refit the model with 20 epochs. To refit the model, you need to specify the model again. You need to add all the needed information to your in R. You need to re-specify the model with all the needed information. Particularly, it's very important to specify the random number seed. You should use the exact same random number seed as your original model. Otherwise, the results will be different. The loss function value will also be different. In that case, the 20 epochs may not be the optimal number of epochs to use anymore. So anyway, remember to specify the same random number seed when you refit the model. And again, this is specification of the model, 2 layers, and this is specification of the optimization algorithm. And this is actually refit the model or estimate the model. Here I just call my new model as model n dot re. So that's a reanalysis or refit of the model. Then after we fit the model to the data, we get the results. We have results saved into our object. One is this one, and another is the model itself. If you take a look at the object, this one, actually you should use not this. So if you look at this model, this output, notice it includes the information like this. First, I give you the information about the last epochs, the loss function value, and the mean absolute error for both the training data and the evaluation data. It also gives you the parameters you used in the algorithm. And most importantly, it includes the matrix you used in evaluating your model. So this is the loss for the training data. This is the mean absolute error for the training data. And then this is the validation loss. Loss for the validation data, loss for the mean absolute error. So why do I choose like 20 epochs? The reason is because I look at my loss here. Notice that when I have this is 22, so this is 21, and this is 20. Okay. Notice that here from here to here, the loss decreased, but from here to here, we cannot see the value exactly here. It actually increased a little bit, so that's why I choose the epochs equal to 20 here. You can look at the values here in the absolute error value. Okay. If you look at the here, if you are interested in like the final model, and then you should look at the here. Okay. And in neural network model, we are interested in estimating the width and the bias. And we can actually get the width and the bias from the results very easily. And there are two ways to get the width. One way is you can use the model and then $some width. So this gives you the width. But those widths are in the tensor format. It's not in the typical matrix format in R. And if you want to change the tensor format to the matrix format, you can use get width function. This directly saves the width into matrix or vectors. For example, if I use get width here, it's better to use like better use moddn.re because that's my final model. And then give you also width. For example, you have a width 6 times 32 matrix, and this is the bias for the first layer. For the second layer, this is the bias for the first layer. Now we have the neural network model, and we have the estimated width. And then we can do a prediction based on the neural network model. Doing prediction again, we feed the input data into the model, and then we see the output data or the predicted value. To do the prediction is similar for neural network analysis as a regression analysis. We basically use a predict function. In the predict function, we can add our neural network model, and then we input our data. And based on data, we can get the predicted value. So that's the predicted value for this input. The input data I use here are the test data. The reason is because I want to do a prediction not using the training data. As we know, if we use the training data, we can fit the training data very well, but at the same time, for the test data, it may not work very well. So here I use the test data. In the regression analysis, I also use the test data to do the prediction. Okay. Now let's take a look at the predicted error. So that's the difference between the observed data and the predicted data. Now I have a mean squared error 0.522. Remember, in our regression analysis, we have a mean squared error 0.518. In our regression analysis, we only have 7 parameters. So here we have 247 parameters. But even though we have a more complex model and we have more parameters, the performance of the prediction is actually not as good as a regression model. So therefore, in selecting a model to do a data analysis, we shouldn't always look for the more complex model or the newest model. We should use a model that fits the need of our data analysis better. So in this situation, maybe like a regression model is a much better model to use than the neural network model. The reason is the regression model is much more simpler, and the prediction accuracy is also similar. And also for the regression analysis, remember we can test the significance of the coefficients. We have the R-square measures, but in the neural network models, notice that we only have the width estimates. We don't really know whether those widths are accurate or not. The reason is in the neural network analysis, the prediction oftentimes is much more important than explanation. So if only we can predict the output well enough, that's good enough. But in social science, we are more interested in probably the interpretation. We are more interested in why that's the case. So therefore, we want to explain the model. Therefore, if you want to test the significance of the coefficient regression model, might be a better model. Our first neural network model is a very simple model. This is a model with just one hidden layer. The hidden layer has 32 nodes. Now let's look at a more complex neural network model. In this neural network model, we are going to have two hidden layers. The first hidden layer has 128 nodes, and the second layer will have 16 nodes. So which means, again, we have input. So X, we have 6X here. The first layer, we have 128 nodes. And then we have second layer, 1, 2, then we have 16 nodes here. Right? And then we have output. All those nodes are fully connected between the input layer, first hidden layer, and among the nodes between the first layer, hidden layer, and the second hidden layer. Okay. So now this model is much more complex than the previous model. Actually, in total, we have close to 3,000 parameters. To specify the model is very similar as the simple neural network model. Again, I set the random seed here. The first layer, 128 nodes, and the input shape is like this. The second layer, 16 nodes. For the second layer, we don't need the input shape. So which means we can simply remove this. And if you add it, the function will simply ignore this. And then the output, we have one nodes. If you take a look at the model, for the first layer, I have about 900 parameters. For the second layer, I have more than 2,000 parameters. And for the third layer, I have 17 parameters. So this is the total number of parameters. Notice that now the total number of parameters are already larger than the sample size. Our sample size is 2,000 for the training data. And to compare the model, again, I set up the loss function to be MSE, the optimizer here. Here, I didn't specify the linear rate. I just use the default linear rate. And again, use the evaluation matrix as mean absolute error. And now I fit my model with 10 epochs. I initially fit the model with 50 epochs, and then I found 10 epochs would give me good results. So I refit the model with 10 epochs. In practice, you can fit the model with 50 epochs first, then the model with 10 epochs again as your final model. Then I'm doing a prediction using my second model. I can see the mean squared error is 0.529. It's slightly larger actually than the simpler neural network model. This is probably because the model overfits the data, so therefore the performance based on the prediction is not as good. The model can be further estimated in improved in other ways. For example, you can use a different activation function. You can even have a more complex model. Another issue with the current data analysis is our validation data set is rather small. We use 20% of the whole data set, but our training data has 2,000 participants. 20% means we use 400 for validation. Okay, this may not be accurate enough. One way to improve this is we can use k-fold validation instead of use a fixed validating data set. K-fold validation means we can divide this maybe like in 5 different folds. Each time we do the validation on one set of data, and for the other 4 folds of data, we use that for parameter estimates. So now we have talked about how to apply a neural network analysis model to continuous data. The active data represents the typical data we would have in social science. We have all the data as numerical data. We have also quantitative data information. But in practice, we know we may also have non-quantitative data. For example, a popular qualitative data or non-quantitative data is text data. Text data are widely available in practice. For example, in our data collection, oftentimes we would ask open-ended questions. How do you feel about a certain situation? How can you evaluate the performance of an instructor? So in this case, the response would be text data. In our next example, we actually use the student evaluation of teaching data to demonstrate how to analyze test data using neural network models. The name of the data set is called setdata.csv. You can download this data set from the website I showed you at the beginning of the workshop. This data set include more than 38,000 records of teaching evaluations. There are only 2 variables in the data set. One is the numerical rating of the teaching. Another is the text evaluation of the teaching. So if you take a look at the data, it looks like this. So again, I use read.csv to read the data set into R. So this is the number of observations, number of variables. So the first variable is called rating. It's a numerical variable. It has value 543, 3.5, 1.5. The second variable is text data. So it's a character variable. For example, the first data point is the text evaluation about the professor, the best professor I've had in college. Only thing I don't like is the writing assignment and so on. Although the keras is very powerful, it cannot process text information directly as in any other software programs or any other method. Now, therefore, the first step here, we need to process the data, process the text data. The idea is we want to convert the text data to numerical values so that we can use the program to estimate the model. In the text data analysis, we need to choose a unit of our analysis first. For example, if we have a text information like this, one unit could be like an individual word. So best, professor, each individual word is a unit of our data analysis. But we can also use the phrase as a unit of our analysis. For example, best professor, writing assignment could be a different phrase to use. We can also use a sentence, the whole sentence here, as a unit of our analysis. In our data analysis, we focus on the analysis of individual words. The method we use here is also called the bags of word method. To use the individual words, we need to split our text data to individual words. To do that, we can actually use this function from the tidy text library. And we don't need to use the library or this function at all because there are functions in keras to process the text data. But I first use this to show you the basic information of the text data. And in this function, we have our data set, and then we have our original data variable. And then the word is data after splitting. By default, this function will split the data into individual words, like best professor I had. And I want to tabulate the unique words, so I use a table function. And then I found I have a little bit more than 10,000 unique words in all my comments. In total, remember, I have more than 33,000 comments. And now I take a look at the most frequently used words here. And there is the most widely used. So it will use more than 50,000 times. And then other widely used words, professor, teacher, take. And among those more than 10,000 words, many of them are only used very few times or even just once in these 38,000 teaching comments. Now, if a word is only used once, maybe it's not very it's not of interest to us. So therefore, in this data analysis, I only use the words that were used at least 6 times in my data analysis. So in total, I found there are about 3,600 unique words that are used at least 6 times. As I just mentioned earlier, keras actually include the function to process text data, the function called layer text vectorization. And you may think about this function as a layer in your neural network model. So we have input, the input will go to this layer, get processed, and then it will be fed into the other hidden layer. So basically, this is the function I'm going to use, layer text vectorization. In this layer, in this function, I need to specify several different options. First, I need to specify n-grams equal to 1. N-gram is equal to 1 means I want to split my data into individual words. And if you use 2, then I will have two words, one word and two words as my data. Then I use max tokens equal to this. The reason is because I want to only keep words that are used at least 6 times. The output mode equal to multi-hot. The idea of this process is originally I have 38,000 comments, right? Now I have 3,608 words, right? So those are the words. Remember, like our text are often very short. So in each comment, we may only have 20 to 30 words. So that means many of those words in this total number of words are not used in individual comments. So what we want to do is we want to create a matrix. This is a 0, 1 matrix. So each row represents one comment. So if a word is used in that comment, I put 1 here. And if a word is not used in that comment, I put a 0 here. So therefore, I can now convert my text comments into a matrix of 0 and 1s. So there's a specification of multi-hot. So I specify the output mode. Okay. I also did some other process in converting my text data into numerical data. For example, I change all the words to be a lowercase. I also remove the punctuations. How to split the data? I split the data using white space. So which means if there's a white space between two words, then the two words are split into individual words. So this is basically the layer for the processing of the text data. Next, I want to get the words in the data. So I can use the depth. What this means is I would apply this vectorization method or text process method to my data. Okay, and then I get all the words. So those are the top 3,600 words used in all my text data. And then I use text vectorization function again so basically this function to change the data into 0, 1 format. And now notice that, so this is the shape of my data. This is the number of rows and number of columns. The number of columns is here because I specify the number of words to keep. So this number of rows is the total number of text in my data set. This matrix is a tensor matrix in the tensor format. It also tells you the types of data. The outcome variable rating is a numerical variable with 9 categories. The 9 categories 0 is 1, 1.125. We can either treat this as a continuous variable or as a categorical variable. Since I already showed you how to do the continuous variable analysis, here I will treat this as a non-continuous categorical variable. So which means I will treat each category as a separate class or separate category. In this case, I want to recode my data using a 0, 1 matrix. This is the process to recode this. I'm not going to talk about this, but I want to point out there's a function in in keras called two category. So this can directly change a category variable to 0 to 1 variable. For example, if for the first one is in the the score is 5, so all the rest is 0, but the last one is 1. Similar for the second comment. For the third comment, so that's 4 here. So I put a 1 here, all the rest are zeros. As in active data analysis, now I also want to split my data into different subsets. In this situation, I split my data into training data. It has 30,000 text. Then I also have a validation data set. It has 5,000 text. And then I have text data. The rest more is about 30,000 text data. Previously in active data, I only split my data into training data and text data. Now I have 3 subsets of data: training, validation, and text and test. I also take out my data set as input and output X and Y for all 3 subsets of data. Notice that in active data, I select the index random. Here, I just use like the consecutive index here. If your data are random, so that's okay. But if your data are not random, there's a particular pattern in your data set. So this is not a good way to do it. For example, if you have data if your data are ordered by the age of the participants, so in this case, this may only choose the participants with a younger age, and this will only choose participants older age. So in this situation, this splitting method may not be good. In that case, you want to randomly split your data. Now I want to specify a model, a neural network model, to analyze this set of data. For this example, I use a model with 2 hidden layers and 1 output layer. In my first layer, I have 64 hidden nodes. The activation function I'm using here is ReLU. It's not a linear function anymore. The input shape, again, I give the number of columns. As we know, the number of columns here should be this. Right? So this is the first layer. Then my second layer is a layer with 32 nodes. Okay. So therefore, if I look at my model, so this would be my input. My input now is much more complex. So I have more than 3,600 input. So my first layer is actually relatively small compared to my input. So I have 64 here. And then I have second hidden layer, 32 nodes. And all of those are fully connected. Then I have my output layer. For the output layer, I have 9 nodes. The reason I have 9 nodes is because we know we have 9 categories. I want to output those 9 categories directly. And I also use the softmax activation function here. The softmax will actually provide the values with everything at together 0. So give you a raw value. So give you the probability for each possible category. You use the softmax. You notice something else here. In my model, I add something called layer dropout. Rate equal to 40.4. Here, rate equal to 0.2. The reason I do this is because if you look at the model, so in the first layer, there's multiply 64 plus 64 width. So this is the total number of widths I need to estimate. So that's a huge number of widths. And in the literature deep learning, people found that you don't really need to estimate all those widths each time for each set of data or in each iteration. What you can do is you can randomly set some of those values to be 0, remove them, drop them out. So that's what I'm doing here. So each time I will randomly drop out 40% of the width. And this will improve the efficiency of your algorithm. And at the same time, it gives you about the same accuracy of the parameter estimates. Now let's take a closer look at the model. For this model, the first layer, I have more than 230,000 parameters. In the second layer, I have a little bit more than 2,000 parameters. And in the third layer, I have close to 300 parameters. In total, this is the number of parameters I need to estimate. So that's much larger than the number of parameters we used in the active data. So that's also why text data is much more difficult to analyze than numerical data. Once we specify the model, next we need to specify the optimization algorithm. I compare the model. The loss function I use is categorical cross entropy. This is because I'm using the categorical data. The cross entropy basically calculated the probability of choosing one category. So this is the optimization algorithm I'm going to use. I also use accuracy to evaluate the model. The accuracy means whether I can predict a particular category correctly or not. With that, I'm going to fit the model. I first tried 15 epochs. The batch size I use here is 200. Notice another difference between the model I'm using here and the active model I used earlier is I specify my activation data instead of using validation split to randomly choose the participants for validation. So my validation data is a data set I set up earlier. The batch size I used again is 200. Each time I input 200 text data to the model. Now, if I look at the loss and accuracy, if you look at the plot, clear the loss is always decreased with the increase of the epochs. Similar, the accuracy always increase with the increase of the epochs. But if you look at the validation data for this plot, the validation loss first decrease as in the training data, and then it increases. Similarly for the accuracy, so it first increase and then decrease. I also print out the values here. And for the loss, keep increasing here, accuracy for the loss keep decreasing, for the accuracy keep increasing. But for my validation loss, notice that after 3 epochs, first decrease and then increase. For my validation accuracy, it first increase for the first 3 epochs and then decrease. So therefore, I decided maybe I should use 3 epochs here to fit my model. So it should be 3. And with that, I refit my model. Again, to refit your model, you need to specify everything again. So now my number of epochs is 3. So how this model will work for the test data? Then I evaluate the model using my text data. So once I fit my model, I can just use the evaluation function. So this is my input for the text data. So this is output of the text data. Notice that I have an accuracy 0.625, which means I can predict that category correctly about 62% of the time. For the comparison, if you use a random classifier, so which means you randomly assign the text into each category, the accuracy is about 11%. So 62% is a large improvement over a random classifier. And with the model, we can conduct the prediction. Prediction basically means, okay, now I have a set of text. I want to know like which number I should assign to it, which numerical value I should assign to it. And so in this case, I use prediction function again. So this basically means for the first row, it basically means for the first text, there I should give 96% of probability to assign a score of 5. And there's some possibility to assign score of 4. For the third text, there's a 40% of chance to assign the score 5. But there's also a large chance, 20% to assign score 4 here. Remember, this is 1, 1.5, 2, and this is 5.